Today we're going to be looking at everyday motion, which is P8 on the separate science course or P6 on the combined course. Our learning objectives today are to describe how to measure distance and time across a range of scenarios, recall typical speeds for those scenarios, and estimate the magnitude of everyday acceleration. Finally, we'll look at ratios and proportion and how these can be used to convert units. First of all, I'd like you to think about how many different ways you can list for measuring the speed of a car, whether that is the passenger, the driver, or possibly the police. How many different ways can we measure how fast the car is going? One option obviously is the speedometer of the car. The police may use speed cameras. You may also be able to tell how fast your car is going from the GPS. And the police with their speed guns can detect the speed of a car. Now I'm actually going to ask you to do something practical and try to measure how quickly an object falls 1 meter. So you're going to take an object and drop it a meter and time how long it takes to hit the floor, and from that try and calculate its speed. Obviously for this you're going to need 3 things. 1, a way to measure 1 meter, perhaps a tape measure. 2, a stopwatch. You have, I'm sure, an app on your phone if you need it. And also an object that's going to be heavy enough so it falls quickly without being so heavy it's going to be dangerous. You're going to repeat this experiment 3 times, measure the time for each and calculate the speed. Once you've done that, you're going to come back and restart the video. So pause the video now and get on with the practical. Hopefully by now you've got 3 sets of results for the time and speed of the falling object, and we can compare those results in terms of precision and accuracy. If all 3 results are close together, we would say those results are very precise, but the reality is in this experiment the chances are we wouldn't get close results, and that's because the apparatus isn't very precise for the very short time periods that we're looking at due to human error. Using something like a light gate would be far preferable, and that's what they would expect you to suggest in an exam. In terms of accuracy, we would expect values of about 0.45 seconds for the time for a falling object, and that's something you can prove yourself if you want an extension task using the equation v squared minus u squared equals 2as. For your next task, I'd like you to create a table just like the one you see below. It should take about an A4 sheet of paper and have enough space on it to record all the details of the instruments used and how the speed is calculated. Don't forget, you can pause the video at any time while you complete the task before moving on to the next slide. For the first option, we're looking at a sprinter running 100 meters, and you can see some of the equipment that might be used. You can measure distance using a trundle wheel or tape measure, and you can measure the time using a infrared light beam gate. For a cyclist, their speedometer works by measuring the frequency of rotation of the wheel. A magnet is placed on the wheel and that is detected by a sensor every time it passes. And then the speedometer uses that to calculate the speed of the bike. One common form of speed camera relies on lines marked on the road at known distance apart. The camera takes 2 photographs very quickly with a known time difference between them, and then the 2 pictures are compared to see the distance that the car has travelled in that time period. One type of speed gun fires pulses of infrared radiation at the vehicle. The vehicle then reflects those pulses back, and the speed gun detects the time difference between when the pulse is sent and when it is received. Car sat-navs use a built-in clock, comparing that to a signal sent out by 3 or more satellites to work out their location. If that location changes over time, they can tell the speed of the car. Here is an example of the answers that you may have in your table. Feel free to read through it and make any amendments or additions, preferably in a different coloured pen. And don't forget, you can pause the video at any time. We talked in the example of the bicycle about how its speedometer works, and I'd like to look at that in a bit more detail. Here we've got a car with a 40 centimetre tyre rotating once every tenth of a second. For this problem, the first step is to work out the circumference of the tyre, which tells us how far the car will travel in one rotation. And for that, we just need to times pi by the diameter of the wheel, pi times 0.4 in this case, giving us 1.2 meters per rotation. Once we have the distance travelled for one full rotation, we can simply divide that by the time taken for one rotation, in this case 0.1 seconds, and it will give us the speed of the vehicle. To give you some idea of how quickly some objects move, a dog or a cat can run up to 30 miles an hour, about the speed of a car through a city. And the cheetah, the fastest land animal, is able to run at 70 miles an hour, which is the speed limit on motorways. Now I want you to try and estimate how fast you walk. Think about how long your stride is and how many strides you might take in a second, and then try and work out how quickly you move. If you're travelling 1 metre in every stride and you take 1 stride a second, then you're probably moving at about 1 metre per second. Remember, this is just an estimate, so don't worry if you're slightly off. Now have a think about how quickly you think you could sprint. Obviously this is going to be different for every person, but just come up with an estimate. About 5 meters per second would be a reasonable estimate, but remember, this is going to be different for every person, so don't worry if your answer is slightly different. Now you're going to try and estimate how fast you could travel on a bike. Again, it's only an estimate, so don't worry if it's not exactly the same answer that I get. A reasonable estimate might be about 7 meters per second for an average cyclist. Now I'd like you to try and estimate how fast an Olympic cyclist might be able to travel. An Olympic cyclist could travel up to 20 meters per second. Now I'd like you to try and estimate the average speed of a car. An estimate of about 22 meters per second or 50 miles per hour would be about average. Using what you've learned about the speed of cars, I'd now like you to try and estimate the speed of a train. You might have something about 56 meters per second or 125 miles per hour. And finally, quite a tricky one, I'd like you to try and estimate the speed of sound. The speed of sound in air is normally about 330 meters per second. Now we're going to move on to estimating accelerations for a car. We'll have a car that's stationary, accelerating up to 27 meters per second, and we will try and estimate its acceleration. Now we have to estimate how long it will take the car to reach its top speed, and I would estimate about 8 seconds. So the time is 8 seconds, and the change in velocity or speed is 27 meters per second. Now to find the acceleration, all we need to do is divide the change in speed by the time taken, so 27 divided by 8, and it should give us about 3.38 meters per second squared for the acceleration. Now I would like you to try and work out how average speed cameras work. These are cameras set up on the motorway at different intervals, and they will work out your average speed between the cameras. Here are 6 statements that explain how the average speed cameras work. All you need to do is rearrange them into the correct order and then write them down in your books. Please make sure you write down all 6 statements fully, and pause the video now and try and rearrange them. And here is the correct order for those 6 statements. So again, pause the video if you need to and check your answers, amend them if need be. And for your final task, all you need to do is copy down the information provided here and fill in the gaps with the correct numbers. Pause the video now and see how you get on. And here are the answers. The first one is 1.6 kilometers times 70 miles per hour, so it's 112 kilometers per hour. Tick it if you've got it right and correct it if it's wrong. For the second one, there are 3,600 seconds in an hour. That's just 60 seconds times 60 minutes. And so the answer is 31 meters per second. 2 kilometers is the same as 2,000 meters. The driver's speed is therefore that 2,000 meters divided by 72 seconds, so 28 meters per second. And this is under the speed limit, so the driver isn't speeding. That brings us to the end of today's lesson, so thank you very much, and I hope you found it useful.